Introduction to Transformations. At the top of this set of notes, we have a table, but we can go ahead and ignore it for now. For this set of notes, we'll be talking about transformations individually, and in the next set of notes, we'll be tackling them all together. So first off, we have vertical translations, which means that the graph moves vertically or up and down. Now, the key here is to first understand that the constant that is being added is added, quote, outside. So we have a constant added or subtracted outside. And when we have a positive constant, the graph shifts upwards, and we have a negative constant, the graph shifts downwards. So here's what I mean when I say outside. First of all, consider the graph f of x equals x cubed. So I'll go ahead and use red for this. And here's a really quick sketch of the parent function. So g of x then, notice that I have f of x followed by a positive 2. Notice the placement of the positive 2 is not inside the parentheses, it's, quote, outside the parentheses. Now, we can take this to mean that we can take the graph of f of x and shift it up by 2, or we can take f of x, but we know that f of x is x to the third, so all I'm really doing is I'm replacing f of x with x to the third, and then the plus 2 is just there. So now we have x cubed plus 2, and again, because that plus 2 is outside the parentheses, what we can do is we can shift the graph up by 2, because that's exactly what adding a number outside the parentheses does. So we take the entire graph, and we'll shift it up by 2. So there's g of x. And then lastly, we have h of x, which is x cubed take away 4. So here we have a negative number that's being added, and this will shift the graph down by 4. The last one was not a very good drawing. Okay, next up we have horizontal translations. So in this case, we have a constant that is inside the parentheses, right? Notice the difference. In vertical, the constant is outside of the parentheses. For horizontal, it's being added inside. Whereas I like to say it's added with the x inside. And this is the one that's a little tricky or counterintuitive. When you have a positive constant, it shifts left, and when you have a negative constant, it shifts right. So taking a look, we have f of x equals the absolute value of x. So again, I'll use red, and then I'll graph the basic absolute value function. Now, g of x is f of x plus 2. So if we think about what we know about function notation, the function itself is an absolute value function, and before it was simply x. Now, function notation tells us to plug what's ever inside the parentheses. What is inside the parentheses? Well, it's x plus 2. So we're going to plug x plus 2 into the absolute value. And so now we have absolute value of x plus 2. Again, we see a positive sign inside of the, I'm going to say per absolute value bars, but you can think of absolute value bars as a special type of parentheses. And so because we have a positive number, this will shift to the left 2. And then lastly, we have h of x, which is equal to the absolute value of correction. I even said left 2, and then I drew the orange graph to the right. There we go. That's left 2, silly Mr. Fan. Now we have the green function, h of x equals absolute value of x minus 4. So this will move right 4. And that's that. Moving onwards, we have reflections. So when we see a negative sign in front of the function, this will flip the graph or reflect it about the x-axis. We do have reflections about the y-axis, but we're not going to worry about those. So part A, we have the square roots of x. So here's my basic square root of x function in red. And so g of x is equal to negative radical x is flipped or reflected about the x-axis. And lastly, we have vertical dilations. So when the function is multiplied by a constant, we will either say that it is being stretched or it is being compressed. And so you don't need to worry about the fancy absolute value bars. All it's saying is, hey, is the number bigger than 1 or less than 1? If it's bigger than 1, it's stretched. If it's smaller than 1, it's compressed. So first of all, we'll graph f of x. So here's the graph of f of x. And so g of x equals 2 times f of x. Well, this turns into 2 times x squared. And so because there is a 2 in front, what's going to happen is the graph will grow twice as big. And because it's growing twice as big, it's being stretched. Now, in contrast, we have h of x, which equals 1/2 x squared. Well, the 1/2 will make it grow half as big. And so what that ends up looking like is it looks like this. Right? It's getting wider. Or if you think of an accordion, if you're pressing them together, it gets smushed and fatter. Okay, and that's it for the set of notes.